Hi folks, and welcome back to Math with Captain Rod. I'm making this video here to answer everybody's favorite question here, or the question on everyone's mind: what is an inverse function? So first of all, let's talk about this stuff I've got above here. So here's a set of elements A, B, and C, which we're going to imagine is the domain of some function. Here's a set of elements 2, 5, and 9, which is we're going to imagine is the range of this function. And the function f is a function that maps elements from this set to elements of this set. And in this example, let's imagine that f of a is 2, f of b is 5, f of c is 9. Right? So an inverse function is a function that maps these elements in the range back to these elements in the domain. Notationally, this f minus 1 of x, this reads f inverse of x. So I'm going to give that function a name, g of x, and that function is the inverse of this function. So if f of a is 2, then our inverse would map 2 back to a. So g of 2 would be a. If f of b is 5, then g of 5 is b. If f of c is 9, then g of 9 would equal c. So graphically how that works is if the point AB is on a graph of f, then the point BA is on a graph of the inverse. So simply put, an inverse function is a function that basically reverses the x and y values. It maps elements from this set in the range back to set elements in this set, which is the domain. Now, if you kind of think about what happens here, since our inverse function is mapping these to these, this becomes the domain of our inverse function, and this becomes the range of our inverse function. An important thing to realize is that, remember, for something to be a function, it has to be one-to-one. If we have a function here, for example, let's look at like y equals x squared. I'm just going to do a quick graph. If we take a look at this, notice that the point, let's say 2, 4 is on this graph. The point negative 2, 4 is also on this graph. Now, this function, it is a function because it passes the vertical line test, but it's not what is called a one-to-one function. Notice if I pick a point here like negative 2, or I'm sorry, 2, 4 and negative 2, 4, we have two elements in our domain that goes to one element in the range. If we kind of reverse that and we try to think about an inverse for this function, the inverse would go through the point 4, 2, but also the point 4, negative 2. Now, if we had an inverse that did that, if f minus 1 of 4 or f inverse of 4 were 2, and f inverse of minus 4 were negative 2, this would not pass the vertical line test, and therefore would not be a function. So there's a requirement for a function to have an inverse that it be a one-to-one function, and I'll go ahead and make other videos demonstrating that example, or talk about what that's all about. Another important thing about inverses is graphically how they work. So let's imagine I've got some sort of function here. Oops, I guess I can't erase it any further. All right, let's get rid of this. Just don't want this in my picture here while we chat. So let's imagine we have a function that goes through the point 1, 2, 3, 0. 1, 2, 3, 4. Well, let's make it 2, 3, 4, 5, 6. I will make it 7, 2. There. 3, 0, and 7, 2. If we were to graph the inverse function, that would go to the point 0, 3. And this one would go to the point 2, 7. Now, if we connect these dots here, these would be connected. So imagine here's my function f of x, like a little linear piece. I'm just making up this example here. If my original function f goes to the 0.30, then the inverse has the 0.03. If the original function goes through 7, 2, then the inverse has the 0.27. Same argument for every point in between. And an important thing to realize, here's our inverse, is that this graph is symmetric about this line. This is the line y equals x. Notice if I take this and reflect it about this line, we get this graph. All right, so let's see if I can summarize this. An inverse function, given some function f that maps these domain elements to these range elements, f's inverse would map these range elements back to these domain elements in basically in reverse order. So for example, if f of a is 2, then f inverse of 2 would be a, like I've got written out here, where g is the inverse of x. Okay. Graphically, another important fact, an inverse function and a function, they're symmetric about y equals x. Another important point, for a function to have an inverse, it has to be 1-to-1, because otherwise its inverse won't be a function. And the last thing I'll talk about in this video is how inverses are found, right? So basically what an inverse does is it basically switches the x and y values. And what we'll do is we'll use that fact to find inverses. So a quick example of that, I'm just going to start with a nice easy linear function. If I take the function y equals 3x, and I want to find its inverse, we would just switch the x and y values, x equals 3y, and then just solve it for y. So y would equal x over 3. So if this is a graph of f of x, or I'm sorry, if this is f of x, this function would be f inverse of x. And please take note a couple of points here, like if I put 3 into this, 3 would get mapped to 9. And notice if I put 9 into this, 9 gets mapped to 3. And if I graph these two equations, y equals 3x and y equals x over 3, they'll be a symmetric, they'll be a reflection of across y equals x. So that's probably enough for this. This was just meant to be kind of an introductory video on inverses. I'll go ahead and make others for finding them. I hope that this has helped. Have a great day.